Okay, here is the second part of 10.2's lesson. Now it's kind of a long one, so I split it into 2 days. Today, for this part of the lesson, we're going to look at what happens if you have a composite function, but the part that you are evaluating is not on the unit circle. So like if you look at this example, it's 5/13, and 5/13 is not in our unit circle, so we can't just use that like we have on the past problems. So in these cases, when you have a number that's not on the unit circle, what we're actually going to do is go back to our SOHCAHTOA. If you remember when we first learned the unit circle, let me pull up my lovely picture I've drawn. The first day I showed you guys how we derived it by making those right triangles and doing, like our opposite over hypotenuse or adjacent over hypotenuse, and that's how we came up with these numbers. We're kind of going back to that idea. If we make a right triangle, we can use those SOHCAHTOA ratios to help us solve each part. So what we're going to do is we always still start on the inside and then we work our way out. So right now we're looking at the inverse cosine, and we know from SOHCAHTOA that cosine of an angle is equal to adjacent over hypotenuse. So if I draw a little right triangle, and let's say this is my angle theta right here, if I'm doing the cosine of that, from this angle, the adjacent side would be down here on the bottom, and the hypotenuse would be up here, and then this would be our opposite side. So if I am taking this ratio, this would be my adjacent over my hypotenuse. So we're saying, given the angle that we're going off of, our adjacent side here is 5 and our hypotenuse is 13. So how this works is, remember, the inverse is giving you the ratio, but then the regular trig function will give you the angle. And so we're kind of working backwards here. They're saying, here's the ratio that corresponds to this angle. So if we're starting with cosine, I'm going to set up my cosine ratio here, but then they're asking us to end in sine. We know that sine uses of an angle equals opposite over hypotenuse, right? So if I have this triangle, if I'm using the same angle for cosine and sine right here, I would be using the same ratios. So I just need to figure out what O is going to be. I already know H, so I can plug that into my sine, but I don't know what O is. But we have a right triangle. So how do we find the sides of a right triangle? We use Pythagorean theorem. So we're going to use the Pythagorean theorem to find that third side. Hopefully you guys remember the Pythagorean theorem. We're going to do a squared plus b squared equals c squared. Remember, c is always going to be that hypotenuse. So we're going to plug in 5 for a. So I have 5 squared. We don't know what b is. We'll just leave that. And then c is going to be 13 squared. And then we're just going to simplify. So this should all be a review, you guys. Hopefully you remember how to do Pythagorean theorem. But we get 25 plus b squared equals 169. And then we're going to minus the 25 over. Oops, I'm going down kind of low. And so that will give us 144. But then again, we need to square root it to get rid of the square. So we get that b is equal to 12. And so that would be our opposite side. So then we literally just plug that in. We're going to say that sine of our angle that we're going off of is opposite over hypotenuse. So we just get 12 over 13. And that's going to be your answer. So not too bad. Just pretty much doing Pythagorean theorem. If you remember your Pythagorean triples, which are just common numbers that you see in right triangles, 5, 12, 13 is one of those common ones. If you recognize that, you could just skip this whole thing and just know that this side has to be 12 if this is 5 and 13. So other common ones are 3, 4, 5, 5, 12, 13 is a common one. Multiples of those would work. So if 3, 4, 5 is one, then 6, 8, 10 would be another one. So you can kind of memorize some of those to even save more time. But let's look at another one. This time again, we're starting with the inside, working our way out. So if we have sine, we know that sine again is opposite over hypotenuse. So if I draw my little triangle here, we're going from this angle. Our opposite side is going to be 6. Our hypotenuse is going to be 11. And then on this one, we're ending with tangent. Tangent equals opposite over adjacent. We don't know what A is, so that's what we're looking for. As soon as I know what A is, I can just do opposite over adjacent, so 6 over whatever this number is. So plugging into our Pythagorean theorem again, we're going to do our two sides. So we'll just say A squared plus 6 squared has to equal 11 squared. Well, 6 squared is 36. 11 squared is 121. And if we minus that 36 over, those cancel, and we get A squared is equal to 85. And then on this one, 85 is not going to be a perfect square. So sometimes they'll let you just keep the square root of 85. If you can, you want to try and do like a factor tree and reduce that and think of a perfect square that goes into 85. I don't think there is one that goes into 85 though, because 4 doesn't go in, 9 doesn't go in, 16 doesn't go in, 25 doesn't go in, 36 doesn't go in. So this one doesn't reduce, so we'll just keep the square root of 85. So that is the side right here. And so then if we plug in our opposite over adjacent, we're going to get 6 over the square root of 85. Again, usually though, we don't like square roots in the bottom, so we'll want to times it by itself on the top and the bottom. Remember, square root times itself, you just get the number back, so we'll just get 85 here. And then we get 6 times the square root of 85 on the top. And then again, if you can, you'd want to reduce it. Only factors, 2 doesn't go in 85, 3 doesn't go in 85, 6 doesn't go in 85. So that one doesn't reduce. We just leave it like that. It's not the prettiest, but it works. Okay. Next one. So on this one, looks like we're starting with sine again. Sine's opposite over hypotenuse. So if we draw our little triangle, our opposite side on this one is 1. And this time, our opposite side is x. We don't even have a number on this. So don't get freaked out when they start throwing variables at you. It's going to work the exact same way. We're still going to do Pythagorean theorem. And we're going to be looking at that outside function to get our answer. So cosine uses adjacent over hypotenuse, so I need to get that adjacent side. So because we're using variables, we're still just going to plug these in. So think of this as A, B, and C in your Pythagorean theorem. We're still going to plug that in so that I get A squared plus B is 1, and then we're just going to have x squared over here. Because it's just a variable, we can't actually take x squared. We're just going to have to leave it. So, well, 1 squared is just 1. So when I start solving for A, we're going to minus that 1 over, which I can't combine. So I'm just going to have to write it as x squared minus 1. That's as far as we can go. And then to get rid of the square, we're going to square root it. That entire thing will get square rooted. So we're going to just end up with a formula or an equation here that A is equal to the square root of x squared minus 1. And that's as far as we can go because we don't actually know what x is, so we can't do anything more than that. So that's going to be our adjacent side, it's the square root of x squared minus 1. So if I do the cosine, remember cosine is adjacent over hypotenuse, we're going to get this lovely thing on the numerator, x squared minus 1. And then our hypotenuse is still just x. And so then that would be our final answer. Okay. So don't get thrown off by having those little x's in there. So this one, our last example, is going to be even messier. If you look at the formula on the inside, we have the square root of x squared minus 9 over x. And we're starting with cosine. So cosine again is adjacent over hypotenuse. So here would be our A over h. So the square root of x squared minus 9 goes on the adjacent side. X is going to go on the hypotenuse. And we're ending with sine. And sine is going to do opposite over hypotenuse. So we need to find that O. Using Pythagorean theorem again, a squared plus b squared equals c squared. Here's going to be our A. We do have a square root, x squared minus 9, being squared. And then we'll just leave b as a b. And then c is x. We square it. So because we have a square root being squared, those just cancel with each other, and we just get the x squared minus 9 by itself. And then we'll just keep b squared and x squared. We can't really do anything with those. So if I'm trying to solve for b, I need to move both of these over. So we're going to minus the x squared over, and we're going to add a 9 over, and we're just going to do this all in one step if that's okay. So those cancel, we get b squared. And then here I have an x squared minus x squared, so those cancel as well. We're just left with a 9, and then we square root that. Well, square root of 9 is 3, so we get b is equal to 3. So that is going to be our answer here. Okay, and then, so on this one, we do have sine again. Sine uses opposite over hypotenuse. I'll write that down. Sine equals O over H. So our opposite side here is 3. Sure this isn't, you guys can see it. And then our hypotenuse was X. So our answer is 3 over X. And that is the end of 10.2. So I'll just write this down here because I think there was some confusion from last time, but 10.2a, this covered numbers 1 through 8 on your homework, and today's lesson, 10.2b, will cover numbers 9 to 15. So you should be able to finish these problems now on that assignment, and that is just going to be due on April 20th. I extended this, so that way you have all of spring break to just take off and have fun, do whatever you want, and then you can come back and you'll have still an entire week after spring break to get this done and ask me any questions. So hope that helps. Let me know if you guys have any questions. I will be doing a Zoom meeting, so feel free to hop onto the Zoom meeting. I'll try to be doing those once or twice a week, and you guys can come and ask questions and just check in with me and make sure everything's going okay. I hope to see you in that Zoom meeting. Have a good day.